A very good morning to all of you. Myself, Dr. P. Hari Krishna, the co-convener of this webinar, on behalf of Medicaps University Indore, I welcome our Honorable Vice Chancellor, Professor Dr. Sunil K. Somani, Registrar, Dean Science, Dean Engineering, and all the HODs, faculty members, and my dear participants, students, and my friends. Today, there is a webinar on quantum physics, the invisible reality. Our our guest speaker is Dr. Shyam Nayak from Badwani. Now, I would request our convener, uh, Professor Dean Dr. Abbas Ali Crosser, sir, to say few words.
Okay, good morning all. Myself, Dr. Kosa. So first I would like to welcome our Vice Chancellor, Dr. Sunil Samani, who is here with us. And then Dr. Shyam Naik, who is our esteemed guest today. And as we can see that the lecture is the invisible reality, quantum physics. So I would like to request all the participants to be listen very carefully this because नाम नहीं लग रहा है कि quantum mechanics, the invisible reality, right? So it will be a very exciting lecture for all you. Just to introduce Dr. Shyam Naik, I would like to say Dr. Shyam Naik has done his research from RRK Indore, and he has a number of publications in his name, and he has been ex-faculty of our Medicaps University also, and also he has guided a number of scholars from IICR, Bhopal, DA Indore, RRK. Many students are under him.
First, I am thankful to Medicaps University, Dr. P. Hari Krishna, Dr. Somani sir, Dr. Kosar sir, Dr. Malaj Das for giving me this opportunity to say something about quantum mechanics. That is the invisible reality. This is my topic of the talk today. The quantum mechanics is invisible reality. This means that quantum mechanics is very important for us in our daily life in all things, but this is not visible. It is invisible. Okay, I am saying something about it. So now I will start. First, the thing is quantum mechanics, the invisible reality. Now I first we discuss about some introduction, what is the quantum mechanics, why and why it is invisible, then some needs of quantum mechanics, then development of milestones of the quantum mechanics, so how it develops, how it comes into the picture, and what is its importance. Then we will discuss some basic phenomena about the quantum mechanics. Basic phenomena means this is the base of the quantum mechanics, and these phenomena are very important for us. Then finally we will conclude. So let me come on the topic. First, I am coming to the topic that quantum mechanics is invisible reality. Initially, what is the mechanics? Mechanics is the branch of physics or science, in general science, in which we will start that something is moving from one place to the other place. If some object is here at this time, then at other time its position will change. Then it is known to be in the motional state. If the position of the object doesn't change with time, then we are telling that object is in the rest state. We will see this motion or kinetics or mechanics in our daily life, such as planets are rotating around the sun. If if we throw a stone from this place, then it will change its position. That is known as the kinetics. Plane is flying in the sky, kite is flying, birds are flying. We are also moving from one place to the other place. So this is known as the mechanics. This we will study in the branch of physics which is known as the mechanics. Initially, in the ancient times or in 17th or 18th century, only classical mechanics are there. Classical means it comes from a long time. Now at present days, we consider the classical mechanics which is based on the Newton's equations. Newton's equations, you are already aware of the Newton's equations, which we now people are studying in the 6th and ninth standard classes. The Newton's mechanics are based on some equations as V is equal to ut plus V is equal to u plus at, S is equal to ut plus half at square, V square is equal to u square plus 2s, and some laws, three laws, which is first is the law of inertia, second is F is equal to m into A, and third is the action reaction rules. The mechanics based on these principles or Newton's law is known as the classical mechanics, and that is sufficient enough for us, because all the motions which we will see with our eyes, which are visible for us, we can explain with the classical mechanics these types of things. Some examples of classical mechanics are that is a free fall under the gravity. If we drop some stone at some place, यदि हम किसी चीज को किसी ऊंचाई से गिराते हैं तो वो धीरे धीरे जमीन पर एक निश्चित एक्सीलरेशन से, एक डेफिनेट एक्सीलरेशन से comes on the ground. That is known as the classical mechanics. So classical mechanics is also referred in some continuous manner, as the position of the stone changes continuously if it freely fall under the gravity. The growing of plants are the examples of the classical mechanics, and many things. Suppose a bus is moving from here and it reaches to the other place, that motion is also explained by the classical mechanics. But if you go through the smaller and smaller object, then quantum natures are there. First, what do you mean by the quantum nature? Quantum nature से मतलब क्या है? What do you mean? The quantum nature, this means that is not continuous thing. It is in some parts. It is not continuous. Suppose the water level increases gradually, so it is a continuous nature. The water from the tank coming out continuously, it is continuous nature. This is not scientifically exactly correct, but this is the example that we will see, that continuous nature, but quantum nature is somehow different. For example, in a class, the number of students are 10. Then if you want to increase the number of students, then they must be 11. After 11, it will be 12. If you want to decrease the students, then below 10, it must be 9, it must be 8, and so on. 10.5 number of students never be possible in the class because it is not fractionable. So this refers somehow to the quantum nature. We have already studied the quantum nature in our previous classes 11, 12, that quantization of electrical charges. The quantization of electrical charges occurs. The charge on any object is in quantized manner. If charge is Q, then it is always plus minus n into E. N is some integer, and E is the electronic charge, which is the charge on one electron. Its value is 1.6 into 10 to the power minus 19 coulomb. See, this is a very small quantity. 1.6 into 10 to the power minus 19 coulomb. Since it is a small quantity, so we cannot see the quantum nature with our eyes, so it is invisible. But electron is a fundamental particle. Fraction of electron doesn't exist in the world. So if you want to create the positive charge on some object, then we need to extract the electrons from there. If you want to create the negative charge on the object, then we need to impart some electrons are there. But we can either give one electron or we can take one electron. Below one electron we cannot give or we cannot take. So charge always increase in the fraction of 1.6 into 10 to the power minus 19 coulomb. This is the example of quantization of the materials. Quantization means it cannot be increased or cannot be decreased below a particular value, and that smaller particular value is known as the quanta of that things. So this is the quanta of the charge. Okay, so this is the quantization. This is the quantum nature. Quantum nature means some minimum amount of that quantity. It is not always occurred in the case of charge. It occurs in the every field, many fields. Every field is based on the quantum nature. So quantization means quantity is in some definite amount. Smaller than that amount is not possible. If you want to increase or decrease the quantity, then it must be increased with that amount or more than that amount. So this is known as the quantization. So, but it occurs only for smaller and smaller values. Okay. Now, the classical and quantum worlds. Classical things we are discussing in our daily lives and we are observing also, but quantum world is not discussed, we will discuss in our daily life. Because in everyday life, quantum effects can be safely ignored because these are very small. But atomic scales, subatomic scales, quantum effects cannot be ignored. If we treat here with classical mechanics, then we get results which are not real or which we not observe in our daily lives. This occurs because these things occurs. Quantum effect हमको daily life में नहीं दिखाई देते हैं, हम उनके लिए बोधर नहीं होते हैं. This occurs because Planck's constant is very small. Its value is 6.6 into 10 to the power minus 34 joule into second. The quantity which is important here is 10 to the power minus 34. If Planck constant has more value, not so small, then quantum mechanics may be applied for the bigger objects. यदि प्लांक कांस्टेंट की वैल्यू इतनी कम नहीं होती, ज्यादा होती है, तो क्वांटम मैकेनिक्स बड़े ऑब्जेक्ट्स के लिए भी अप्लाई की जा सकती. Although it can be applicable for bigger objects, but it is senseless. So it is senseless, but everything is based on the smaller and smaller objects. Suppose quantum mechanics works for the atomic particles, electrons, protons, neutrons. It doesn't work for the bigger objects, for a cricket ball or a stone. It doesn't work. It works, but calculation using the quantum mechanics for bigger objects is not significant. Why, we will discuss later. So it is, since the base of the bigger object are also smaller objects, so quantum mechanics is the base, the law is the base of the all mechanics. Quantum mechanics or quantum world is invisible for us because it is beyond the capacity of our eyes. We cannot see these smaller particles, proton, electrons, neutrons, fermions with our eyes, and we cannot see their motion. So it is invisible for us, but everything is generated using that things. Everything is consisted of atoms, everything is consisted of neutron, proton, electrons, and other smaller particles. So quantum effects are very important for us because this is the base. Okay. Now, classical mechanics works for the bigger particles, but if we grow, here already discussed, if you go for smaller and smaller particles, then quantum mechanics appears there. The development of the quantum mechanics for initially was done by the Bohr, Heisenberg, Schrodinger, and other peoples. These are for very small particles. Here in classical mechanics, some principles as the Newton's law, Galilean transformations are working here, but if we go through the smaller and smaller particles, then this law doesn't work. Some new laws are there, which we will discuss later. Okay, but this is comes into the quantum mechanics. Now, classical mechanics also doesn't work for very high speeds. In daily life, we are seeing the particles which are moving with some velocity as 40 meter per hour, 40 meter per second, or 100 kilometer per hour, or 200 kilometer per hour, or 300 kilometer per hour. We are not seeing the in general daily life the object which are moving with the very high speed. So classical mechanics is applicable. Classical mechanics is also not applicable for the particles which are moving with very high speed. Very high means the speed of light. It is the highest possible speed in the world. No material particle or no particle can move with a speed which is greater than the speed of light. See, its value is 3 into 10 to the power 8 meter per second. This means 3 lakh kilometer per second. It is very 3 lakh kilometer per second. It is very high speed. So if you go through this speed, then again classical mechanics or Newtonian mechanics doesn't work. A new types of mechanics is there, which is known as the relativistic mechanics, which is developed by the Einstein in the 19,000. Developed by the Einstein. This is known as the relativistic mechanics. If both things are common, means particles are very small, but they are again moving with the speed of light. Then a new field is there. This theory is known as the quantum field theory, and which is given by the Dirac, Pauli, Feynman, and other peoples. So quantum mechanics is important here, which are very small particles as proton, neutrons, and electrons. For bigger particles, although it works, but its results are same. Now, what is the boundary between quantum and classical mechanics? So, classical mechanics is simple. Simple means we can calculate the properties of the objects, position, momentum, force, kinetic energy, and other things using the classical mechanics for bigger objects, for macroscopic objects. But as we go through the smaller and smaller object, classical mechanics doesn't work. A new types of mechanics which is known as the quantum mechanics which works there. Quantum mechanics works for the microscopic objects. So what is the boundary? Now, it starts from the quantum mechanics. Initially, de Broglie in 1924 give the concept of the dual nature of the matter. Initially, it is known that some phenomena of light, it starts from the light. Some phenomena of the light can be explained only on the basis of the classical nature or particle nature. Particle nature means light is a bundle of packet of energy. But some phenomena can be explained on the basis of the quantum wave nature. So light is same thing, but sometimes it behaves like a wave, and sometimes it behaves like a particle. So de Broglie told that at that time in 1924 that light, not only light, but all particles behave like a wave and like a particles. Sometimes it behaves like a particle and sometimes it behaves like a wave. But he again also told, Bohr told that at that time, if a particle is behaving like a wave, then at that time it doesn't behave like a particle. But if behave like a particle, then it doesn't behave like a wave. So that is the boundary between the classical and quantum treatment. Okay, so that is given. De Broglie told that every material particle which has momentum p is associated with a wave. That wave is known as the matter wave or de Broglie wave. The wavelength of the de Broglie wave is given by h is equal lambda is equal to h by p. Here h is the Planck's constant, which value is 6.6 into 10 to the power minus 34 joule into second. Its value is 6.6 into 10 to the power minus 34 joule into second. Its value is very small. So this wavelength is known as the de Broglie wavelength of the particle. Now Bohr's correspondence principle is there, which told that if the dimension of the particle is smaller than its de Broglie wavelength, suppose particle is there, so it must have some wavelength, some momentum is also there. So if we know the momentum of the particle, then we will calculate the de Broglie wavelength. So if the dimension means size of the particle is smaller than its de Broglie wavelength, then quantum mechanics is applicable there. Classical mechanics cannot give the correct result. Again, if the de Broglie wavelength of the particle is greater than the size of the particle, de Broglie wavelength badi or particle chota hai, then quantum mechanics is there. But if the size of the particle is greater than its de Broglie wavelength, then quantum mechanics give the same result as given by the classical mechanics. So this decides the size of the particles, for which classical mechanics and quantum mechanics give the same results, and the particles for which quantum mechanics and classical mechanics give different results. So it decided by the de Broglie wavelength. If de Broglie wavelength is bigger, and de Broglie wavelength is smaller, then we need to use the quantum or classical mechanics. For bigger particles, for which de Broglie wavelength is small. It is senseless to calculate the quantum mechanical phenomena, quantum mechanical expressions. For example, if we can also write the Schrodinger equations and quantum mechanical treatment for a cricket ball, but it gives same results as given by the classical mechanics, and the calculations in the classical mechanics are rather simpler, are very simpler compared with the calculation in the quantum mechanics. So we will apply the classical mechanics there, but for smaller size of particles as proton, electron, neutron, spark, other particles, we need to, or we forced to apply the quantum mechanics, because classical mechanics doesn't work there. Now, to explain some phenomena for smaller numbers of particles, at that time in early 20th century, some phenomena are observed, are there. This is black body radiations, photoelectric effect, Compton effect, atomic spectrum, atomic linear spectrum, in which we observe the Lyman, Balmer, Paschen, Reckitt series. Specific heat of solids at lower temperature. So these phenomena are there which cannot be explained at that time by the classical mechanics. So we need to go through the quantum mechanics. We can explain the black body radiation successfully by using the quantum mechanics, photoelectric effect proposed by the Einstein's equations and other things, Compton effect, atomic spectrum, specific heat of solids at lower temperature can be successfully explained by the quantum mechanical phenomena. Classical mechanics is not sufficient enough. For example, black body radiation. Black body radiation is explained by using the Planck's hypothesis. In black body radiation and photoelectric effect, Compton effect, atomic spectrum, the involved particle which is responsible for this phenomena is photon. Photon is a particle of, photon is also known as the quanta of electromagnetic field. It consists of energy h into nu, where h is the Planck's constant and nu is the frequency of light. So if we consider this Planck's hypothesis, then we can explain black body radiation and this phenomena also. Using the classical mechanics, we cannot explain. Now we are coming to the development, because at that time in 19th century, the quantum mechanics is not there before this quantum mechanics is not there, only classical treatments are there, but some phenomena at that time arises are such that they cannot be explained by the classical theory. So quantum mechanics is there in 1900 times. The Planck's give the Planck's theory. He told that at that time the light consists of small bundles or packets of the energy. These bundles or packets are known as the photon. The energy is h into nu. After that, Einstein explains the photoelectric effect in 1905. He gave the famous equation which is known as the Einstein's photoelectric equation. Planck and Einstein also got the Nobel Prize for that. In 1913, Bohr also proposed a atomic theory about the structure of the atom. He told that electrons are revolving around the nucleus in some definite orbits. That definite orbits are known as the stationary orbits. When electron revolve in this orbit, then it doesn't decay its energy. On the basis of this Bohr theory, atomic spectra, linear spectra can be explained successfully, in which different series as Lyman, Balmer, Paschen, Reckitt series are there, can be explained successfully, although some drawbacks are there. But nowadays, Bohr's theory and the quantum mechanics which we are using here is known as the old quantum theories. New quantum theories are also there. This is proposed by the Bohr at that time. In 1914, Frank and Hertz also do some experiments which proves that the electrons in the atom also has quantized energy. This means every value of energy is not possible in the atom, but some discrete energy levels are possible in the atom for electrons, which is further quantized by other peoples. In 1917, quantum theory of radiation is given by the Einstein. Einstein also gives some view about the stimulated types of emissions. He told that only not spontaneous emission are there in the world, but some other types of emissions are also present in the world, which is known as the stimulated emission. He gave the Einstein's A and B coefficients, which we have already studied in our 12th standards and in BSc also. Stern-Gerlach experiment is there in 1922. Stern-Gerlach also proves that not only the energy, not only the angular momentum, but magnetic moment is also quantized in the atoms. He take the aluminum atom for that. He passed these aluminum atoms, beam of aluminum atoms by from the magnetic field, which varies with the position. He got that aluminum beam is splitted into two parts, which proves that the value of magnetic moment has two values, and it is also quantized. So he proves that magnetic moment is quantized. Bohr proves that energy is quantized. Although this means quantum natures are there. Now, Compton effect in 1923. In Compton effect, what happens? A photon strikes with the electrons, and there is some inelastic collision between these two. There is some exchange of energy between the photon and electron. So this is also the proof that photon, which is a bundle of packet of energy or which consists of lights, also behaves like a particle, and it is also quantized. De Broglie gave the dual nature in 1924. Pauli in 1925 proposed the exclusion principle, which is very famous for the fermionic systems. According to Pauli principle, the total wave function of a fermionic system is antisymmetric. We can also tell that in a system, two same particles never get the same energy, or never all four quantum in atoms. We can tell the all quantum numbers of two electrons never be same. This is the Pauli exclusion principle. In 1925, Schrodinger proposed the famous equations, which is known as the Schrodinger's equation. These equations have same values in the quantum mechanics as in classical mechanics Newton's equations have. We are calculating the other things or explain the behavior of the particles by considering the Schrodinger's equations. These are very famous equations, but these are also applied non-relativistically. If the speed of the particle is very high or relativistic speed, then we need to go through the other equation, which are known as the Dirac's equations and Kelvin-Gordon equations. Schrodinger also proposed, also gives some explanation for the wave functions, which we use in the equations. Wave function is a characteristic. We will discuss further. The explanation of wave function given by the Schrodinger is not correct at that time, but correct expression is given in 1926 by Max Born. Max Born give the correct explanation of the wave function. Then Heisenberg proposed the uncertainty principle in 1927. He told that at that 1927, he told about the inaccuracies in the various types of measurement. And Dirac again proposed the concept of the antiparticles and negative energy states in 1928. On this basis, he again give the explain, he again gives some basis of the negative energy states and propose that some particle also exist in the world, which is known as the antiparticles. Although at that time antiparticles are not there for the electrons in the world, but in 1932, after 4 years, Anderson discovered a particle which is the antiparticle of electrons. So this again supports the Dirac's concept. So these are the development of the quantum mechanics in from 1928. From here to here in 30-40 years, these developments occurs. Now again, आवाज आ रही मेरी? Hello?
सर आ रही है सर आपकी आवाज?
Okay, sir. Okay, so this is the development of the milestones of the quantum mechanics. This means this give a sufficient base to the quantum mechanics that quantum mechanics must exist in the world. These are the milestones that we need to treat these things quantum mechanically, because here Planck's theory is the proof that light is quantized. This means you see it is in small bundles or packets. So we must treat the light quantum mechanically. As we see the photoelectric effect is now used in various types of solar systems. The photoelectric effect is the base of solar systems. Various types of experiments as photo are based on the photoelectric effect is XPS, EXAF, OJ electron spectroscopy, which are the base of research about the structure of the particles and base of research today, structural research today, based on the quantum mechanical behavior of the light, which is known as the quantum mechanical behavior of the light. Now Bohr's theory is again gives the correct results, which cannot be. We told that the energy is also quantized. Here he told that the angular momentum, magnetic momentum is also quantized. So a large number of quantized quantities are present in the world. But again I am coming the things that it is invisible. Quantum mechanics is invisible because this occurs at very low levels. These occurs at very low level. This is not applicable for bigger objects because the value of Planck's constant is very small. Again, I am telling that the Planck constant is very small value, 10 to the power minus 34 joule into second. If this constant has bigger value, then these mechanics can be applied for these mechanics. We need to apply for the bigger particles. But since value of Planck's constant is very small, so we see the effect of quantization is same as the effect we got by the classical treatment for bigger objects. Okay, now I am coming to some particular particular topics which is important in the quantum mechanics. All the topics cannot be discussed here because the quantum mechanics is a very wide field. So I am discussing some basic things as Schrodinger equations. Schrodinger equation I am discussing here because it is the base. Initially, if we start the study of to study the quantum mechanics, then initially we read the initial things which we want to study is the Schrodinger's equation. Schrodinger equation is proposed by the Schrodinger in 1925. He is giving these types of equation. In these equations nothing is there. This psi, this symbol is known as the psi. This is known as the wave function of the object. This is nothing but the operator which is known as the total energy operator in terms of the time, I h cross del by del t. Here h cross is the Planck's constant, h cross is h by 2 pi. Its value is 1.05 into 10 to the power minus 34 joule into second. I is under root minus 1. This shows the rate of change of psi with respect to time. H is an operator which is known as the Hamiltonian operator, and psi is the wave functions. But first, if you want to discuss some phenomena, or if you want to get the explanation of some things, some systems, for example, for hydrogen atom, then first we write the Schrodinger equation for that systems. If we want to get the some explanation about the simple harmonic oscillator, then first we need to write the Schrodinger equation for that systems. We write the Schrodinger equation for that system, then we solve the Schrodinger equation and get the wave functions and other things. That is the procedure. That is the procedure or methodology which we adopt to explain some things by the quantum mechanics, quantum mechanical functions for a smaller number of smaller size of particles. We first, wave function is there, wave function is psi. This is the methodology which we generally adopted to extract something using the quantum mechanical systems. So psi is wave functions. Then we put some dynamical operators or dynamical variables or operators. For example, in quantum mechanics, every very observable means the quantity, physical quantity which we observe, which we measure. For example, we measure the momentum, so there is some operator for the momentum. If position is, we will measure the position, some operator is for position, some operator is for force. Operator means it is some mathematical tool as del by del t. As Laplacian operator del 2 upon del x square plus del 2 upon del y square plus del 2 upon del z square. This is the Laplacian operator in terms of the Cartesian coordinates. If you want to study some different coordinate system, see the coordinate system which we choose is based on the simplicity of our calculations. It is also based on the symmetric of the object. For example, if you want to study the hydrogen atom, then we will never accept the Cartesian coordinate system. We will accept the spherical coordinate system. In this way, because at that potential is spherically symmetric in case of hydrogen atom. So if we do the calculations in that spherical symmetrical systems, then it is easier for us to get the results. Then we put the dynamical law, write the equations, put the essential dynamic operators, then we get the probability density which we get from the wave functions, the normalization, expectation value, and transition probability, etc. we will get. So first we write the Schrodinger equation for that system. For example, we will study in our previous classes that the particle in a box. A particle is confined in a box of length A. So what are its positions, its energy? What are its momentum? What is its other properties? That to obtain these quantities, we need to first write the Schrodinger equation for that, then we solve Schrodinger equations. Schrodinger equation is of two types. First is the time dependent Schrodinger equation and second is time independent. In the time dependent part, time is here, wave function varies with time, but the time independent part, this doesn't vary with the time. The discussion in very detail is not possible due to the time restrictions. So I am again coming to the other part, wave function. Wave function is the characteristic of the state of the system. For example, if you want to study the hydrogen atom, then wave function is specific for each state. For first s, if electron lies in the first s position, first s orbit, then wave function is have some definite value. If it is in the 2s system, 2s energy level, 3s energy level, 2p energy level, then these all different energy levels have different wave functions. So the state of the hydrogen atom is characterized by the different wave functions. अलग अलग सिस्टम की अलग अलग स्टेट के लिए अलग अलग वेव फंक्शन होता है. वेव फंक्शन से हम उस सिस्टम की उस स्टेट में किसी प्रॉपर्टी को निकाल सकते हैं. For example, we want to get the energy of the hydrogen atom in the first s state. Then we write the wave function for first s state. Then we will use the operator for the energy and get the psi star operator of the energy psi. Then we will get the energy. In this way, we can calculate the energy of the hydrogen atom in the first s state. If we want to get the energy in other state, then we need to wave function of that states. In a similar way, if we want to get the momenta of the system or hydrogen atom in first s state, then we need to use the that operators. This is the procedure. This is general procedure. Some property of wave functions are that it is related to the matter wave. Initially, I have talked that de Broglie proposed that every massive particle has a matter wave associated with. हर massive particle के साथ एक wave associate होती है. That wave is known as the matter wave. So matter wave is expressed by these wave functions. Psi is finite, continuous, and single valued. It is normalized, and degeneracy and orthogonalness is also there. Psi completes define the motion of the particles. If we know the psi or wave function of that in that state, then we can calculate all other properties of that state of the systems. Now, some particular popular problems which you have studied in the quantum mechanics using the Schrodinger equations and other calculations are the free particle, how the free particle behaves, what are the energy states of the free particles, then particle in a box, potential step and potential barrier, reflection and transmission of the particle, tunneling of the particle from the potential barrier. Tunneling is also very important phenomena. which we have studied. Now there are some researchers are also going in this field. Tunneling. You are already aware of the alpha, beta, and gamma radiations from the atoms, that is known as the radioactive radiations. These also happens due to the tunneling effect. Tunneling effect means if some potential barrier is there, then particle tunnel this barrier. Alpha particles lie inside the nucleus. It fills a high field at the surface of the nucleus and it crosses that barrier. This is known as the tunneling effect. Now, harmonic oscillator problem is there. Angular momentum theory is well known in the quantum mechanics, which gives some good results. Spherical symmetric potentials as hydrogen atom, scattering phenomena, and theory about the radiations are the popular problems which we have studied in our bachelor classes, master classes, and researchers, and in somehow some little in the 12th standard also. Now, Planck's theory. This is the Planck's law. This is the initial law at that time. So I am again coming to this point, that Planck's quantum theory. Yes, you have already seen, because this also give the invisibleness of the quantum phenomena. We will saw that the light is emitted from the electric bulb and tube lights and other things. We will see that light is emitting out from the bulbs continuously. Bulb से जो light निकलता है वो लगातार निकलता है, but we are seeing that continuous निकल रहा है. So we don't need to go through the quantum mechanics here, but light is emitting. But light is emitting due to the quantum mechanical effect. How light is emitting from the bulb? Light is emitting from the bulb because quantum mechanics involved there. If we flow the electricity in the filament of the wire, then what happens? If we flow the electricity in the bulb, then what happens? So it becomes hot, and if it becomes hot, then electrons goes in the excited state as is shown in here. And if electrons goes in the excited state, then it cannot remain there for long time. It goes into the ground state or below energy levels fastly within 10 to the power minus 8 or 10 to the power minus 23 second time interval. So difference in the energy is emitted from the photon, which is given by E is equal to h into nu. Nu is the frequency of emitted photons, and h is the Planck's constants. So light is emitting from the bulb, which we are seeing in our daily life, but we don't bother about the quantum mechanics. But this is based on the quantum mechanical phenomena, that electron is making a transition from the higher energy level to the lower energy level, and the corresponding difference in the energy is emitted in the form of photon. So this is invisibility of the quantum mechanics here. Again, Heisenberg uncertainty principle is there. In 1933, he proposed a principle. He gave a principle that it is impossible to measure the object, two quantities of the object, momentum and position, with 100% accuracy. If the inaccuracy is delta x in the position and inaccuracy in the momentum is delta p, then their product must be greater than h upon 4 pi. But this is become significant in case of smaller objects, because value of h is very low. This can again, as we can also tell in the angular momentum and angular position. In the case of rotational motion, delta x is the angular position and delta p is the angular momentum. So product is again greater than or equal to h cross by 4 pi. So this is proposed by the Heisenberg, and Heisenberg also got the Nobel Prize in 1933 for that. You can also write in terms of the energy and time. Delta is the energy and delta is the time. The inaccuracy in the measurement of these two must be, sorry, symbol is not correct here. It is greater than the h cross by 2. Symbol ulta lag gaya yahan pe. H cross by 2. So this is the Heisenberg uncertainty principle, which this is not applicable in case of bigger object. Why? Because for bigger object, the de Broglie wavelength is smaller than their size, so it is not significant there. But this is not visible. So small variation in the small position and time is not visible for us. Suppose in the electron, this gives some correct results which we observed in our daily life. Suppose we are already we are already aware about that emission of beta particle from the nucleus is there. Beta particle is nothing but an electron, but electron not is a nuclear particle. So how it comes from the nucleus? If it is not a nuclear particle, then how it comes from the nucleus? So about that, we give a proof that electron not is a nuclear particle, because if electron lies inside the nucleus, using the uncertainty principle, if electron lies inside the nucleus, then its energy must be greater than 8 MeV, million electron volt. But emitted beta particles has energy not more than 1 MeV or 2 MeV. So electron is not a beta particle, it doesn't lie inside the nucleus, but it emits due to some other phenomena which is known as the weak interactions. The correct explanation of this is given some later after giving the Heisenberg uncertainty principle. The explanation of that is like this: the neutron is converted into a proton by emitting one electron and one anti-neutrino. Neutrino is also a smaller particle and quantum mechanical particle. Neutrino is very small, its energy is less than 10 eV. It is not detectable by some instruments also, which we detect from alpha, beta and gamma particles, but some special types of detectors are used to detect the neutrino. But neutrino again gives you some important informations. For example, the information about the core of the sun is obtained only by the neutrinos, because neutrino is a particle which cannot interact by the electromagnetic and other gravitational interactions. It only interacts with the weak interactions. If a photon is generated inside the core of the sun, then it takes thousands of the years to come to the surface of the sun. यदि एक फोटॉन जो है, अगर हम फोटॉन को ले सन के कोर के बारे में इंफॉर्मेशन लेने के लिए फोटॉन को चूज करें, तो वो इंफॉर्मेशन हमको नहीं मिल सकती है, क्योंकि सन के कोर में जो फोटॉन जनरेट होता है ड्यू टू द इलेक्ट्रोमैग्नेटिक इंटरेक्शन इट कम्स टू द सरफेस फर्स्ट, इट नीड टू कम टू द सरफेस. सबसे पहले उसको सन के कोर से उसके सरफेस पर आना पड़ेगा, एंड सरफेस पे आने के बाद ही वो हम तक आ पाएगा. तो सन के कोर में जो फोटॉन जनरेट होगा, इट टेक्स थाउजेंड्स ऑफ ईयर टू कम टू द सरफेस ऑफ द सन. वो सन के सरफेस पर आने में हजारों साल ले लेता है, बिकॉज इट इज वेरी डेंस एंड वेरी स्ट्रॉन्ग इलेक्ट्रोमैग्नेटिक फील्ड्स आर देयर. तो वो भूल ही जाता है कि वो कहां से आया था, और जब उसको खुद में ही वो इंफॉर्मेशन नहीं होगी तो हम उससे वो इंफॉर्मेशन कैसे लेंगे. बट न्यूट्रिनो इज ए पार्टिकल विच कैन नॉट बी इंटरेक्टेड बाय इलेक्ट्रोमैग्नेटिक एंड ग्रेविटेशनल इंटरेक्शंस. न्यूट्रिनो एक ऐसा पार्टिकल है जो कि इलेक्ट्रोमैग्नेटिक और ग्रेविटेशनल इंटरेक्शन के थ्रू इंटरेक्ट नहीं करता है. दैट्स व्हाई इफ इट इज जनरेटेड इनसाइड द कोर ऑफ द सन, देन इट comes out to the surface and comes to the earth, and we are detecting here. So the information about the core of the sun consists in the neutrino which we got. न्यूट्रिनो में जो सन के कोर के बारे में इंफॉर्मेशन रहती है हमको मिलती है. न्यूट्रिनो इज आल्सो नोन एज द डार्क मैटर. न्यूट्रिनो को डार्क मैटर भी कहते हैं बिकॉज इट इज नॉट इजीली डिटेक्टेबल. ओके, सो दिस इंफॉर्मेशन वी गॉट ड्यू टू द क्वांटम मैकेनिकल फिनोमेना एंड क्वांटम मैकेनिक्स. बट information is true, but quantum mechanics is not visible for us. Now again, by using the Heisenberg uncertainty principle, we again get some things as some informations which are true. Again, atomic model is there, classical model doesn't explain. This is something given by the Rutherford, as the electron is revolving around the nucleus. If classical mechanics is applicable there, so electron is negatively charged, which is revolving around the positively charged nucleus, so it must have some acceleration. Due to the acceleration of negative charge, it radiates some radiations. Due to these radiations, the energy of the electron decreases with time, and if energy is decreases, then its radius decreases, and finally it fall into the nucleus by following a spiral path as is shown here. This is proposed by the Rutherford, but this is the classical in nature, but quantum nature is there. If this classical nature is here and quantum nature doesn't exist, क्वांटम नेचर अगर यदि होता ही नहीं तो ये ट्रू होता, और इसके कारण से एटम का अस्तित्व ही नहीं होता। एटम डजंट एग्जिस्ट, बट एटम इज हाईली स्टेबल। एटम परमाणु जो है वो हाईली स्टेबल है, पुराने समय से अभी तक चला आ रहा है। देयरफॉर quantum nature is responsible for that, and for our existence and other objects existence, quantum nature is there, therefore atom is stable in the nature. The explanation is that electron lie in the stationary orbit, we previously told, and due to the stationary orbits it doesn't decay its energy, so it is stable in nature. The energy is not only quantized, but direction and orientations of the orbits are also quantized. We have already discussed. So we cannot see these things. Orientation of electron orbits, this quantization we doesn't see, but we see the existence of the atoms. We see the existence of other materials from a very long time. So this shows that although quantum mechanics is invisible, but it is real. Okay, so these are the some other Dirac equations also. With this I finish my talk here. If you have some query, you can ask.
Thank you very much, sir, for your valuable explanation about quantum mechanics. Now I request the participants, anyone among the participants, if you want to ask any question, you can raise your hand. Anyone among the participants who want to ask anything? Please raise your hands. Yes, Kamran, you can ask the question.
So you mentioned dark matter, and you said that this is just neutrinos. Can you explain a little more about dark matter,
Hello?
please?
Your voice is not clear.
Sorry, sir.
What, please?
Sir, am I audible?
Shyam sir, he's asking about the neutrino.
Yes. What thing?
न्यूट्रिनो के बारे में पूछना चाह रहे हैं, about the neutrino.
Okay. लेकिन क्या चीज पूछना चाह रहे हैं?
सर न्यूट्रिनो आपने बोला था कि डार्क मैटर के नाम से भी जाना जाता है.
Yes.
तो डार्क मैटर ही न्यूट्रिनो है या फिर मतलब उसमें और कुछ भी कंस्टिट्यूट होता है, या फिर मतलब किस तरह से? सर थोड़ा सा कंफ्यूजन है वहाँ पे.
डार्क मैटर सुनिए. डार्क मैटर, we are telling the dark matter, most universe is consist of the dark matters. Dark matters means which is not detectable easily. डार्क मैटर उसे कहा गया है यहाँ पर जो कि आसानी से डिटेक्ट न हो. As proton, neutrons and other proton and neutrons are easily detectable. Proton, neutron और दूसरे अल्फा पार्टिकल्स, बीटा पार्टिकल्स are easily detectable. हम उनको आसानी से डिटेक्ट कर सकते हैं. Are you getting my points?
Yes, sir.
But since neutrino has very less mass, its mass is smaller than 10 eV. See, electron is lighter particle. इलेक्ट्रॉन हल्का पार्टिकल है. इलेक्ट्रॉन का मास है 0.5 MeV, million electron volt or mega electron volt. It is 10 to the power 6. Are you getting my points?
Yes, sir.
It is 10 to the power 6
You can ask the
electron volt.
question.
But mass of the neutrino is very small, less than 10 electron volt. So it is very difficult to detect the neutrino. So the neutrino are present in the universe. We cannot detect that. Even that are present, then our range is not that we can detect that neutrino are present here. That's why it is known as the dark matter, because it is not detectable. We cannot detect, but it is present there. वो होता है लेकिन हम उसको डिटेक्ट नहीं कर सकते, इसलिए हमने उसको डार्क मैटर बोला. आर यू गेटिंग माय पॉइंट्स?
Yes, sir.
Thank you, sir.
Information about the core of the sun we can obtain by the neutrino, because न्यूट्रिनो से इसलिए मिल जाती है क्योंकि न्यूट्रिनो सन के कोर में अगर जनरेट होता है तो सन के कोर से, सन के केंद्र से वो सरफेस पे आके हम तक आ जाता है. लेकिन न्यूट्रिनो में न तो मास है न ही उसमें कोई चार्ज है. तो वो तो इलेक्ट्रोमैग्नेटिक फील्ड से भी इंटरेक्ट नहीं कर सकता और ग्रेविटेशनल फील्ड से भी इंटरेक्ट नहीं कर सकता, तो वो इजीली आ जाता है। लेकिन अगर फोटॉन अगर सन के कोन में जनरेट होता है, लाइट फोटॉन, तो सिंस सन कंसिस्ट ऑफ वेरी लार्ज ए वेरी स्ट्रॉन्ग इलेक्ट्रोमैग्नेटिक फील्ड, सूर्य में इलेक्ट्रोमैग्नेटिक फील्ड बहुत ज्यादा स्ट्रॉन्ग है, तो सरफेस तक आते आते उसको हजारों साल लग जाते हैं। यहाँ पे एब्जॉर्ब हुआ, फिर इमिट हुआ, फिर एब्जॉर्ब हुआ, फिर इंटरेक्ट हुआ। इन दिस वे इट लॉस्ट इट्स इंफॉर्मेशन। कोर में जो इंफॉर्मेशन थी वो उसके पास खत्म ही हो जाती है। एंड इफ इट वंस इट कम्स टू द सरफेस देन इट कम्स टू द, पहले वो सरफेस पे आएगा फिर हम तक आएगा, तो हम तक आते आते उस सारी इंफॉर्मेशन इसकी लॉस्ट हो जाती है। दैट्स व्हाई वी कैन गेट द इंफॉर्मेशन अबाउट द कोर ऑफ द सन।
Thank you very much, sir, for your valuable answer. Now, may I request Dr. Malias Das, sir, to give the vote of thanks to Shyam Naik, sir. Shyam Naik, sir, आप आपका screen sharing बंद कर दीजिएगा, please.
Okay.
Good morning, everyone. Myself, Dr. Malias Das, Head of Department of Physics, Medical University, Indore. It is my pleasure to present the vote of thanks for today's webinar on quantum physics on the behalf of the department and on the behalf of the Medical University, Indore. First, I thank our resource person, Dr. Shyam Naik, Assistant Professor, Government College, Barwani. He shares his valuable knowledge with the participants about the important concepts of the quantum mechanics. It starts from the concept, what is the motion, what is the rest, and then the different terms of the quantum mechanics. Thank you, sir. We are thankful to our Honorable Vice Chancellor, Sir, Professor Dr. Sunil Keswani, for their kind motivation and administrative permission. I would also thank to our Registrar, Sir, Dean Engineering, Sir, Professor Dr. D.K. Panda, Sir, Professor Dr. Diti Jain, Dean Sciences, for their enthusiastic support. And very special thanks to our organizing committee, our Professor Dr. A. Kosar, is the convener, and the Professor Dr. P. Hari Krishna, co-convener of the program. Our heartfelt thanks to all the participants for active participation in this program. And with these warm words and a kind message, I move to end of this today's webinar. And thank you, sir. Thank you. Over to Dr. P. Hari Krishna.
Thank you very much, sir, and thank you all participants for your presence for this wonderful webinar by Dr. Shyam Naik, sir.